In this lecture, we are going to discuss about Coriolis component of acceleration. So we already discussed acceleration diagram for slider crank mechanism and 4-bar mechanism. In that case, we consider a ball rotating about a fixed point. In that case, we need to find out two acceleration, radial component and tangential component. So there is no problem with this kind of concept. But there are some cases in which the object, so here consider this ball as a slider where the slider will rotate about this point. At the same time, the slider will slide inside this slotted bar. So this is slotted bar. So in that case, we need to consider the Coriolis component of acceleration. So that is what here it is given. Whenever a slider slides along the another rotating link, such as quick return mechanism, then the Coriolis acceleration must be calculated to find the tangential acceleration. So there are two types of acceleration, A tangential and A radial. A radial equal to R omega square, A tangential equal to R alpha. So this is the formula to find. So using these two formula, we can find A tangential, A radial for a component like this. But for these cases, we cannot use this formula. Say for example, we can use A radial as it is, but A tangential we cannot use this formula. So for that we are going to use A tangential equal to 2 times of V into omega. Here V represent velocity of slider, omega represent the angular speed of slotted bar. So A tangential of quick return mechanism, we can consider this as Coriolis component. So the Coriolis component equal to 2 times the velocity of slider multiplied by the angular velocity of the slotted bar. So let us consider this example. AC Coriolis component equal to 2 times of V into omega. So there are 4 cases. This is slider and this one is slotted bar. When the slotted bar rotate anti-clockwise direction, when the slider moves in the upward direction, then the Coriolis component of should be towards left direction. Anyway, we are going to use this condition in the next problem. So here the condition is when the slotted bar rotate in anti-clockwise direction, meanwhile the slider slide towards O, that is in the downward direction, then the Coriolis component of acceleration should be towards right. So this is common sense. Say for example, when the slider moves downward, a slotted bar rotate anti-clockwise, then the Coriolis component always away from or towards right hand side. So this is we can easily identify through common sense. So let us directly go to one simple problem. So a mechanism of crank and slotted lever will be given here. The crank rotates in counterclockwise direction like this at 120 rpm. We need to find velocity and acceleration of ram d, and we also determine the angular acceleration of the slotted lever. So that is this one. We need angular acceleration of this slotted bar. So the dimension are given: AB 150 mm, OC 700 and CD, so this one 200. Here the given data, so N already given 120 rpm. From that we can find omega, so that is 12.57 radian per second. So from that we can find the known velocity component, VB equal to R into omega. Here R is equal to AB. AB value already known, 0.15 meter multiplied by 12.57 should be 1.97 meter per second. Then our final aim is to find VD, AD and alpha OB. That is, so now our final aim is to find the angular acceleration of the slotted bar. So let us start with configuration diagram. Take A3 sheet, divide it into 2 half. First draw a vertical line of OA, the length of the line 400 mm. From point A, draw an inclined line which makes 45 degree from the horizontal vertical line. So this is point B. So this is point A. So AB 150 mm. Then from point O, draw an inclined line which passes through point B. So this is B dash. So see the difference. B on AB, whereas B dash on OC. So the length of the OC 700 mm. So there is a difference between B and B dash. So the point B dash on B, but the point B connected to A, whereas the point B dash connected to O. So that is a difference. Again from point A, draw a horizontal line which is 300 mm. Then from point C, draw an arc of 200 mm. Then mark point D. So this is the configuration diagram for given quick return mechanism. Now I am going to apply law of relative velocity, where I have to draw a perpendicular line for each link. So link 1 OA, which is fixed, so there is no need to draw velocity component. So first I am going to draw the velocity component for crank AB. So this is perpendicular. Before that, let me erase this point. Okay, next OB dash. So this is perpendicular to OC. Then velocity of slider along the line of stroke. Then VCD, which is perpendicular to CD. So totally I have 1, 2, 3, 4 components. So now I am going to move all these components to my velocity diagram. Okay, first identify the fixed point O and A. So this is my fixed point O and A. We already calculated VB equal to 1.9 meter per second. We assume that value as 6 centimeter. From that, 1 centimeter equal to 0.316 meter per second. We are going to use this conversion factor later. Next I am going to move the line VB. Before that, we can move VD. Since it is a velocity of slider, it will be along the line of stroke only. So I am going to move the line VD. Next I am going to move the known velocity component, that is VB. The only difference is here the velocity known, that is 6 centimeter. Whereas VD only direction known, velocity unknown. So the point B is known. Next I am going to move the point C, VC. So that is connected this line, the point connected to O. So we can keep this line like that. That's it. So now we have B. I need to find B dash. So the point B dash on OC. So the point B dash lies somewhere on this line. So this is point B dash. So how do you find the line B dash? Here the condition is the line B dash in velocity diagram should be perpendicular. So that is the condition to be satisfied for a point B dash on configuration diagram. The point B dash both are same on configuration diagram. Hence the only way to identify these points on velocity diagram is both lines should be perpendicular. So here I have B. So draw a line which makes 90 degree with respect to this line. So from that we can find one point. So that is nothing but B dash. Okay, so now we can identify the point C, because the point C on along the line of OB dash. So here we have OB dash. So we have a point C somewhere here. So how to identify the point C? For that, once you say, for example, I identified that this is a point C. Once you identified C, then you can apply this condition. VCD should be perpendicular. So we can find D also. Let us see how to find the point C. For that, condition is OB dash, so OB dash known divided by OC unknown on velocity diagram equal to OB dash on configuration diagram. So OB dash, we can measure this value, OB dash. Then OC, so OC 700, so this is 700. We need this value. So when you rearrange that, we can easily find the point C. Once we identified the point C, we can easily mark point D. So our final aim is to find VD. Now measure VD. You will get some value multiplied by in centimeter. Multiply that value into 0.316. You will get 2.15 meter per second. So this is how you can find the velocity of ramp. So this is subdivision 1. Next, omega CO, so that is angular velocity of slotted bar. We need this value to calculate Coriolis component. So omega CO equal to VCO divided by CO. Again VCO we can measure. So from this point to this center. So 2.15 meter per second divided by 0.7. CO value 0.7. So you will get this value. So that is my omega CO value. Next, I'm going to draw the acceleration component. To draw the acceleration component, we need some values like radial component value. First, I will draw the acceleration component, then we will come back to here how to find the radial component of different points. So let us consider the same configuration diagram. So in this diagram, now I'm going to draw the acceleration component. So acceleration component always parallel to link. So this is fixed link. Then for AB, so this is AB. So for that, acceleration component should be AB, because since it is a rotating crank rotating at constant speed, there is no need of tangential component. So it has only radial component. We can take that radial component as AB. So there is no problem with that. Then here, so this is AB dash. So B dash is a point somewhere here. So it should be along the line of slotted bar. So AB dash, second acceleration component. Here this is radial component. Similarly you have to find tangential component. Then A acceleration of component of slider, so AD. So slider has only one component. There is no separate tangential radial component for slider. So there is no problem. Whereas here acceleration of link CD, it has two components. So this is radial component. Again tangential component should be perpendicular. Again it has here it is perpendicular. Okay, so that perpendicular component is nothing but here. Apart from that, for BB dash we have to consider one Coriolis component. So Coriolis component is nothing but tangential component, ATC. So we can take it as AC, Coriolis component, to be considered for point BB dash. Why we are considering that component? Because the point, the slider slide as well as rotate. So we are considering extra point, AC. So this is how we have to, these are the component we are going to use. So how do you find the AC? So AC equal to 2 into V omega. Omega is nothing but angular velocity. V is nothing but velocity of slider. From that you can find a Coriolis component. Whenever a point rotate as well as slide, then we must calculate Coriolis component. Here the point B dash on B rotate as well as slide. So we are calculating Coriolis component. So what are the radial component we need to find? So A radial of B dash, then A radial of DC, then A radial of AB. So totally we need 3 radial component and 1 Coriolis component. So totally we need 4 component. So let us go back to velocity diagram. So now we are going to calculate the 3 radial component and 1 Coriolis component. So the first radial component, A radial of, so it should be like this, A radial of AB. So formula for radial component, V squared of corresponding link AB divided by AB. So VAB value already known, 1.9 meter per second, divided by AB length also known, 0.15 meter. So from that, A radial of BA 23.7 meter per second square. So next one, A radial of DC. So this component. So A radial of DC equal to velocity square of DC divided by DC. Again DC value 0.2 meter, VDC. So this is VDC. So measure this value, convert into meter per second, and then divided by DC, you will get 1.01 meter per second square. So 2 radial components are over. Then the third radial component here, A radial of B dash O. So A radial of B dash O equal to V squared of B dash O divided by B dash O. Again B dash O, this is the value, divided by B dash into O. So this value we can measure. When you divide, so B dash O 520 mm. So use proper scale. So you will get 4.62 meter per second square. So that is your A radial of B dash O value. So now we calculated all 3 radial component. We need only one more value, that is A Coriolis of PB dash. So that is nothing but 2 times of omega. So omega is nothing but omega CO, then VBB dash. So we can measure VBB dash from here. So this is VBB dash. Then omega CO is nothing but VCO divided by CO. Again VCO. So this is point C. So VCO means we have to measure this distance. So VCO divided by CO. So CO value 700.7. So 2.15 divided by 0.7. This should be in meter per second. So normally you will get some values in centimeter multiplied by this 3.316 meter per second. You will get 2.15 divided by 0.7. You will get this value. So if you consider this value here, the Coriolis component of BB dash equal to 6.45 meter per second square. So this is how you have to calculate all these values. So it may look little bit difficult, but let me tell you how to understand the concept clearly. So this is the acceleration components, right? So AB, there is no problem. It's a true component. AD also there is no problem, but we have a problem with ARB dash and ARDC. Again, we don't know the value of, we can easily find AB, because AB known velocity we can easily find acceleration, but we don't know the value of B dash. So with the help of AB and O, we are trying to find B dash. With the help of B dash, we are trying to find C. With the help of C, we are going to find D. So this is a logic you have to remember. I will tell you once again. There are 4 acceleration component, 1, 2, 3, 4. 4 and 1, there is no problem. 4 just horizontal. A true component, there is no tangential since it is rotating at constant speed. So AB. Again for 2, you need to find radial as well as tangential component. Again for 3, you need to find radial as well as tangential component. So how we are going to do all those things? First, with the help of A, O point and B point, we will try to find B dash. With the help of B dash, we are going to find C, because the point C lies on B dash O. So we can easily find C. Once you find C, you can directly find D using this relation. So that's what we are going to do. So let us see how to draw the acceleration diagram one by one. Diagram like this. So now I am going to draw acceleration component. Acceleration component always parallel. So this is A radial of B. there is no tangential component, so we can take it as AB. Then this is a acceleration component of B dash O, so along the line of OB dash. Then acceleration component of slider, always line of the stroke along. Then A radial of DC, again we need to draw a perpendicular line for this. So that's it. Now identify the fixed point, O on A fixed point, so we can take O on A as fixed point. First I'm going to move the A radial of B. The reason is A radial of B value is known, 23.7 meter per second square. We assume that value is as 6 centimeter. So that is what scale factor says, that from that 1 centimeter equal to 3.95 meter per second square. Next we can move the slider component, because this is always going to be along this dot line. So next I'm going to move slider. So two components already over, A radial of B, A radial of A of D. So we have two component. So what I am going to do is, so A known value, B known value. So I'm going to find B dash, that is P double dash. From that I am going to find C. From that I am going to find D. So next, the Coriolis component, as we discussed in the first two slides. So the Coriolis component act in this direction, because the slider move downward direction, then the entire system rotate anti-clockwise. So the direction of Coriolis component towards right. So this is the direction. So now I'm going to copy this line from here to here. So this is a line. So this is tangential component. So Coriolis component normally represent tangential. Then how do you find radial? So radial, tangential, both are perpendicular. So we can draw a perpendicular line for that. That's it. Next I'm going to move this line AB dash, which is connected to O. So I'm going to move this line here. So this is a radial component again. And before that, the tangential AC value, we already calculated AC value 6 point something. So from the scale factor you convert that value as here, and this is perpendicular, just this line will go like this. Again A radial B dash we already calculated, so from that you can take this values as fixed. Again draw a perpendicular line to this, so both will cut at a point. So we find B. So this is going to be B dash. Since it is an acceleration diagram, we are going to represent it as B double dash. Actually it is B dash. From this B dash represented here. Okay, now we calculated B dash. Next we need to find C. So the point C lies along OB dash. So here I have O, here I have B dash. So extend this line. So the point C will be somewhere along this line. So it's going to be here. Okay. So sorry, here. Now the question is, how do you find C dash? So you can use the ratio of triangle. So I need OC dash. So OC double dash. So this is OC. Yes, OC dash divided by OB dash equal to OC divided by OB. So OC value is 0.7. OB value also we can measure from the diagram. Then OB dash known. When you substitute, you will get OC dash value. So we are measuring OC dash. So from that we will get C dash as this point. Then the last component, here we have A radial of DC. So move this point to C like this. This is a radial component. Again we need to draw a perpendicular component. So again AR DC we calculated already. So it will cut D somewhere here. So this point is called AD, acceleration of tangential component. So this is how you can draw the acceleration diagram for quick return mechanism using Coriolis component. So from this values, by measuring, we need AD value. So AD is nothing but just measure A and to this point D. So you will get AD value. Similarly, you have to find out omega of angular acceleration. So alpha of OC. So that I will leave it to you. So you have to find alpha OC by yourself, whereas here I calculated AD. If you that AD value is nothing but measure OD multiplied by a scale factor of 3.95 meter per seconds, you will get AD value square. So this is how we can draw a velocity diagram, acceleration diagram for quick return mechanism using Coriolis component of acceleration. The main reason for using Coriolis component of acceleration, there is a point in which the link or the slider rotate as well as slide, like quick return mechanism. So in that case, we need to find Coriolis component instead of conventional tangential acceleration. So with the help of tangential operation, finally we calculated the we draw the entire acceleration diagram for quick return mechanism. Thank you.